Right, so today we're going to finish our discussion on potentially connected degree sequence, okay? So the reason that we studied potentially connected degree sequence is because originally we have the graph realization problem where we're given a degree sequence and we want to find a graph that matches the degree sequence, okay? So for this problem, we've already come up with an algorithm. Okay, so today we're going to modify this algorithm a little bit. Okay, so let's first recall the details of the algorithm. So first of all, recall that the input for the problem is just a degree sequence. So you have a series of degrees. Given the series of degrees, immediately we can know how many vertices do we need, okay? So we first create the desired number of vertices that we need. So that's step one. And then we're going to repeatedly pick vertex and pick the neighbors for the vertex, okay? So step A, so crucially, for step A, we can pick any vertex we want, okay? But when we pick their neighbors, we have to be careful, okay? So we need to choose the neighbors that has the highest remaining degrees, okay? And then the rest is easy. We just add edges between the vertex that we pick in step A, and we add edges between this vertex and the neighbors, okay? So that's how we solve the graph realization problem, okay? But a small drawback for the algorithm is that the output may be a disconnected graph, okay? So this motivates us to study this following question, that is, we want to find a kinetic graph, okay? So the problem or the degree sequence is called potentially connected if we can find one kinetic graph to realize it, okay? So recall that we don't need that all graphs that realize it are connected, no. All we need is just one, okay? One is enough. Okay, so for example, like this degree sequence, just 6 twos. So for this degree sequence, obviously we can use this disconnected graph, okay, which consists of 2 cycles, okay, or 2 triangles to realize it. Or we can just use 1 cycle, which is connected, okay. So we want this and not this, okay. So last week we didn't discuss an algorithm to find such a graph, such a kinetic graph, okay? But what we did is that we discussed a necessary and sufficient condition for a potentially kinetic degree sequence. So in order to get a kinetic graph, first of all, we have to make sure that there are no isolated vertices, okay? In other words, all degrees are greater than 0, okay? So at least one neighbor for every vertex. And also you need to have a sufficiently large number of edges. And when translates to degrees, this means the total degree needs to be large enough. And I think there's a very simple observation that we had last week, that is any kinetic graph has a spanning tree, okay? And if you have a spanning tree and you have n vertices, then the number of edges in the spanning tree must be n minus 1, okay? So if we are considering total degrees, then if you have n minus 1 edges, this means you have twice or 2 times n minus 1 total degrees. Okay, okay, so I think this is a quite natural, sufficient and necessary condition, okay? So we've discussed the proof last time, and today it seems like, or we're going to find an algorithm to construct a connected graph if the degree sequence satisfies these two constraints, okay? 所以我们上礼拜有去谈这个 potentially connected 的 degree sequence，目标就是我们不只是希望拿到一个disconnected graph，我们希望我们拿到的手上的 graph 是 connected，OK？所以我们就去看这个 potentially connected degree sequence。然后我们上礼拜有说，如果你要你的图可以变成是 connected，你必须要满足两个条件 ，OK？ 第一个条件就是所有的 degree 都至少是1，换句话说，每一个点至少都有一个邻居。然后另外一个条件是total degree 必须要够大，就是你的总的边的个数要是够大 ，OK？ 然后另外要强调一下，就是我并不是说只要满足这两个条件，就一定可以拿到 connected degree 一定可以拿到一个 connected graph，OK？ 就前提是我们的前提就是它已经是 graphical。OK， 就是我已经保证可以至少有一个 graph， 也可能是 disconnected，OK， 但至少一个 graph 可以满足这个 degree sequence。在这个前提之下，我们才会去讨论说能不能拿到一个 connected graph，OK， 所以这个条件先决条件还蛮重要的，因为我们等一下基本上包括我们上礼拜在谈一样，都是假设这个已经是 graphical 的 degree sequence。OK， 好，所以那我们上礼拜要给一个 proof， 但是我们今天不会去看那个 proof， 所以我不知道到这边大家有没有什么问题。这个等于是上礼拜的内容，那我们会类似接续后续的讨论。有问题吗？OK， 如果没有的话，那我们就开始今天的内容。Okay, so yeah, I think we can start with an example. Okay. Okay. So I think we can stick with the old example that we've considered before. Okay. So let's try to find a graph, a kinetic graph, to realize it. Okay. So basically, we're going to follow the previous algorithm. So we start by creating 6 vertices, and we have their remaining degrees. Okay. So in the previous algorithm, there's only one space where we can further modify it. Okay. That is in step A. Okay. So in the previous algorithm, we can pick any vertex as this Vj. Okay. Okay, so let's assume that we first choose V1, okay? So this is our vertex picked in step A, okay? And according to our algorithm, we have to choose neighbors, in particular 3 neighbors, and these 3 neighbors must have the highest degrees. So we're going to add edges like this, okay? All right, so this is step 1. Oh, sorry, the first round. All right. And suppose in the second round, we pick this as Vj, okay? So the remaining degree is 2, so we have to find 2 neighbors. And let's suppose, because now we have ties, okay? So all the other vertices, they have remaining degrees 1. So let's assume that we pick these 2, okay? So this is round 2. Okay. Now in the third round, let's pick this, okay? So this is Vj, so we have no choice but to add this edge, okay? Okay. So this apparently is not a kinetic graph, okay? So the problem or the question that I want to ask is, what's wrong here? So if you want to modify the algorithm, how would you modify it? Because apparently this is not our desired output, okay?我们刚刚做的事情是，刚刚至少在这个 example 里面，我们先在每一步，我刚刚特别都是挑 degree 最大的那一个 ，OK， 然后就是 step A， 挑完 degree 最大之后，那基本上就 follow 演算法，然后演算法就是你去挑剩下 degree 最大那些 ，OK， 然后就一直做，哎，当然发现其实如果你是这样做的话，这个 graph 就不会是 connected， 就不是我们想要的。所以现在问题是你要怎么样修改刚刚那个演算法，才可以让它变成是 connected graph， 让它的 output 变 connected。So I think intuitively the reason that the previous algorithm fails is because in step A we choose high degree vertices, okay? And because in step B, we're going to choose high degree neighbors. So what happens in the future rounds is that like in the end of this algorithm, we're going to have some small degree vertices remaining. And they have no choice but to connect to each other. So they cannot be connected to their the large component we've already built, okay? So it's like this. We have some degree 1 vertices, and they are forced to connect to each other instead of this large component here, okay? Which results in a disconnected graph, okay? So to avoid this, in step A, instead of choosing the highest degree, we're going to choose the smallest degree, okay? Okay, so step A, let's choose this one with degree 1, okay? So because the degree is 1, we have to find one neighbor, okay? But step B specifically tells us that we have to choose this guy, which has the largest neighbor, okay? Which has the largest degree, sorry. Okay. So now we see that we've solved the issue that this small degree vertices, they cannot be connected to the main component of the graph, okay? So that's the first round. And in the second round, sorry, let me modify, create a new slide. Okay, so in round 2, we're going to pick this vertex, once again because it has the smallest degree, and we're going to choose this vertex as the neighbor, okay, because it has the largest degree. Okay. All right, so then we have a tie, okay, so you can actually pick any vertex you want, okay, because the only graph to realize 2, 2, 2, 2 is a cycle or a square, okay? So it doesn't matter which vertex you choose, doesn't matter which neighbors you choose, you're going to end up with a cycle, okay? But anyway, let's see, okay? So find 2 neighbors, so we can pick this one and this one, okay? Okay. No. Okay. All right, so once again we have a tie, so let's choose this one. So this is VJ, and we have to choose the largest degree. Okay. Okay, now we have our last round. So we can only add an edge like this, okay? So now this is a connected graph, okay? So let me modify the algorithm. Okay. Okay, so yeah, just a small modification. When we choose the vertex in step A, we always choose the smallest one, okay? Okay. But this is just an example, okay? We want to convince ourselves that whenever the degree sequence is graphical and it satisfies the two conditions we have, these two, we want to make sure that our algorithm always outputs a kinetic graph, okay? Because apparently if the degree sequence does not satisfy these two conditions, we cannot find a kinetic graph, okay? But on the other hand, we're not sure whether if the degree sequence satisfies these two conditions, our algorithm will always output a kinetic graph, okay? So we need a proof, okay? Okay. So I won't give you like the complete proof, okay? Because I want to just show you the most critical part, okay? So you see, during the execution of the algorithm, we keep simplifying the degree sequence. First, we have the original one, 3, 3, 2, 2, 1, 1. If you still recall, we have the notation D and D prime. So D refers to the original degree sequence, and we have D prime, which is the modified or simplified degree sequence, okay? So the key point is to show that, so if initially we have a potentially kinetic degree sequence, like this, okay? So this is a potential kinetic degree sequence. I want to make sure that this new degree sequence is also potentially kinetic degree sequence, okay? Because if this 2, 3, 2, 2, 1, 0 is potentially kinetic, and our algorithm can find a kinetic graph for this, then adding these two will still give us a kinetic graph, okay? So let's consider, oops. Let's consider the counterexample we have to illustrate my idea. Okay. So for the previous algorithm, which failed to produce a kinetic graph, the way we simplify the degree sequence is like this. Okay, so we pick the first one as Vj, So the new degree sequence becomes, so this is D, the new degree sequence is 0, 2, 1, 1, 1, 1. Okay? Now this 0 is not important, okay? Because in the future we don't have to consider this, okay? So the key part is to consider this, okay? So is this potentially connected? Well, there are two ways to find out, okay? So first you can try to draw a kinetic graph, okay? Because this is quite easy. And the second way is to apply the necessary and sufficient condition we have. That is to test whether we have isolated vertices. That is to test whether all degrees are at least 1. So checks, okay, all degrees are at least 1. Next, we have to make sure that the total degree is large enough, okay? So the total degree should be 2 times a minus 1, okay? So imagine that you have a 5 vertex graph. So in order for 5 vertex graph to be connected, it must have at least 4 edges. So in order to have 4 edges, you have to have at least 8 degrees, okay? So the total degree should be at least 8, okay? But now the total degree is only 6, okay? So it fails. So total degree less than 8, okay? So this is not potentially connected. Okay, but the original one is, okay? Okay, and if you want to use the first method to find out whether it is potentially connected, you can just draw a graph, okay? So you have a vertex with degree 2, so you can choose any one of them to be the vertex with degree 2. So now this has degree 2, and this has degree 1, degree 1. So to realize the graph, the only way is to use this graph, okay? This is the only graph can realize it. And this is not connected, okay? So this is not potentially connected, okay? Okay, so yeah, so if this new degree sequence is not potentially connected, it means for the rest of the graph, it can be disconnected. So we cannot guarantee that the final output will be connected because the remaining part will be disconnected. And yes, perhaps you can use these edges, these 3 edges to make it connected, but we're not sure, okay? 所以刚刚说的事情是，如果我们刚刚考虑的是前面那个演算法，就是我每次都是挑那个在 step A 都挑那个 degree 最大，它会发生的事情就是这个新的 degree sequence， 它就有可能会从本来是 potentially connected 就会变成不是 potentially connected。OK， 那这样的问题就是，如果它不是 potentially connected， 那就代表它建出来的 graph 一定不是 connected graph。OK， 所以我们刚刚都已经有画出来了，所以我可以把这个边加上去，所以它画出来的图就会是长这样子。OK， 你会看到这个蓝色的图，它事实上是没有连在一起的。OK， 所以即便你再加上这3个边，因为最后的 output 不是只有这个蓝色的边，还有本来在这个 round 加的这些边，即便你把这些边加上去之后，它一样这边是断掉。OK。 However, if you apply the correct algorithm, okay, so for the correct algorithm, we'll start with the rightmost vertex, okay? So we have this edge. So D prime will be 2, 3, 2, 2, 1, 0, okay? But once again, we can ignore this 0, okay? Okay, so this 2, 3, 2, 2, 1, is it potentially connected degree sequence? So once again, there are two ways to figure it out, okay? So the first way is to try to draw a graph, okay? And in particular, try to draw a kinetic graph, okay? And the second way is to test whether the two conditions are satisfied. So apparently all degrees are at least 1, check, okay? And then we have to count the total degree. So we know that the total degree should be at least 8, okay? And what's the total degree here? So the total degree here is 10, okay? So check. Okay, so two conditions, all satisfied. So this is potentially connected, okay? Okay. So we can try to mimic the previous card example. So let me draw the graph here. Okay. So this blue graph is a kinetic graph that realizes these three edges here, 2 edges here, 2 edges here, and 1 edge. Okay. So this blue kinetic graph realizes this highlighted degree sequence. Okay. So if this can be realized by a kinetic graph plus this edge, which connects this edge, this vertex to this already connected graph, the whole graph will be connected. Okay? So I think this is the most important idea for the proof. That is, if the original degree sequence is potentially connected, you want to make sure that after simplifying it, the new degree sequence is still connected, is still potentially connected. Okay. So in some sense, the proof is quite similar to the one that we try to analyze the correctness of the algorithm. Okay, so I want to show that if the original degree sequence is graphical, then the simplified degree sequence is also graphical. Okay. But I think this time the proof is much easier compared to the previous one. Okay. Okay. So we're going to prove if D satisfies, I'll just write 1 and 2, okay? So these are the two conditions. These two? No. These two, okay? then d prime also satisfies 1 and 2. Okay. So that's our goal, okay? So I want to prove that this is true, okay? So you can see that if we keep applying this, okay, so starting from the original degree sequence, we'll keep shortening the degree sequence because whenever we do a round, we get degree 0, we're going to remove it. So the length of the degree sequence will be shortened, okay? So like in the last round, we'll have just like 2 degrees, okay? Which in this case must be 1, 1, which means you can use just one edge to make it connected. Okay, so, and then you just reverse this process, you know that if the last round we get a connected graph, and you know, so all the previous rounds will get a connected graph, okay? So the whole picture looks like this. Okay, so let's suppose round K is the last round, okay? And if you want to be precise, I think, how many rounds do we have? I think it should be m minus 1. Okay. Okay. So for this last round, if it is potentially connected degree sequence, the only potentially connected degree sequence we can have is 1, 1, okay, which can be only realized by this graph, which is connected, okay? So no matter which algorithm we use, it will output this one, okay? Okay, so this is the last round. So let's try to like replay the whole process, but in the reverse direction. So in round n minus 2, we're going to add some edge, okay, to this graph, okay? And in round 3, once again, we'll add some edges and so forth. Okay, so this is like the core of the graph, which is connected. And if you look at in the reverse direction, you're going to see that we keep adding edges to a connected graph. So the whole graph will be connected. Okay, 所以就为什么刚刚这一步是最关键的，就是如果我可以确保说一开始的是 potentially connected degree sequence， 那这样子最后一个一定也会是 potentially connected degree sequence。但是在最后一个 round 的 potentially connected degree sequence 基本上没什么好说的，它只有可能就是1，1而已，因为如果到最后只剩2个 degree， 然后它们又要是 potentially connected， 那唯一的可能就是1，1。那1，1不管任何的演算法，它唯一去 realize 它的方法就是这个一个 edge，OK， 所以你可以把它想成这个一个 edge 就是我们刚刚看到的这个蓝色的这个 ，OK， 只是我们是把它只看最后一个 round，OK， 那你会看到我们刚刚这个蓝色做的事情是我们会再加一些红色的边，直接加到这个 connected graph。那你把一些边加到一个已经是 connected graph， 整个一样会是 connected，OK。所以就是如果你去倒转这刚刚我们 看了这个演算法的执行过程，就比较像是我们一开始最底层是已经有一个 connected graph， 然后我们不断加边连到这个本来就已经是 connected 的 graph 上面，所以整个 graph 到最后就会是 connected。OK， OK， so it all boils down to this key claim. OK。OK， so Okay. So this is the original degree sequence, where delta stands for the smallest degree, and d prime is the new degree sequence. Okay. So the reason we get this is because we always choose the smallest degree, and whenever we want to find neighbors, we always choose the largest degrees. So for these largest degrees, we're going to subtract 1 from those degrees. Okay. And here I just ignore the last 0. Okay. Okay. Okay, so here we have to consider 2 conditions. So the first one is no isolated vertex. Okay. In other words, all degrees are at least 1. So this means we have to show the following. Okay, so we have to prove that if for the original degree sequence d1, d2 up to dn, they are all at least 1. We want to show that this d prime, all degrees are still at least 1. 本来的，如果我告诉你说这些 degree 本来都是至少都是1，我要去说明说，这个新的 degree sequence 一样，至少每个都是1。所以要怎么说明这件事？ OK， 所以像这里 OK， 所以33221这个本来都是1，我们要说明的是这个荧光的部分，确实如你至少在这个 example 里面会看到每一个都至少都是1 ，OK。So there are 2 parts in the degree sequence. Okay, so this green part, we do not change it. So if their degree is at least 1 in D, and obviously because we don't change it, so their degrees, these degrees are still at least 1. So we don't have to worry about these degrees. But we do need to consider these degrees because now they are less, okay, than the original degree. Okay. So the only case that we have to consider is it possible that some of them, D1, D2, up to D delta, the original degree is 1. So if any one of them is 1, then 1 minus 1, you get 0, okay, which violates the first condition. Okay. So is it possible that D1, D2 up to D delta, is it possible that any one of them is 1? 有没有可能就是前面这些 degree 最大这些都是不一定都是，就是其中至少有一个是1。因为如果其中一个至少是1的话，你这边再减1，就会让它变成是0。 那如果它是0的话，就会违反刚刚的我们要说明的这个没有 isolated vertex 这个限制。有没有可能本来这个是1？没关系，我们先因为刚打中，我们休息一下，大家可以想一下 ，OK？ 所以你的条件就是本来的这个满足1跟2，就是没有 degree 是0的，这是本来的，然后total degree 至少是够大 ，OK？ 这2倍的 n 减1。 All right, okay. So okay. So let's first show that in D prime there's no zeros. Okay. So anyone has any idea? 要怎么说这个新的 degree sequence 一定不会有0？为什么至少一定都会有1？有想法吗？ Okay, so let me give you a hint, okay? So we're going to consider two cases, okay, depending on the value of delta, okay? So let's first consider okay, so let's first consider the case where delta, which is the smallest degree, is at least 2, okay? So if delta is at least 2, is it possible to find a 1 in D prime? 如果最小 degree 至少都是2，那有没有可能在你调整之后，有一个 degree 是0？ So 对，所以为什么？ Exactly. So because every degree is reduced by at most 1. Okay. So if originally the degree is at least 2, then after we modified, the degree is at least 1. Okay. So if delta is at least 2, this means all degrees in the original degree sequence is at least 2. Okay. And because we at most minus 1, so all degrees in the new degree sequence is at least 1. Okay? All right, so this is case 1. And the other case is when the smallest degree is 1. Okay? So if the smallest degree is 1, is it possible to have degree 0 in D prime? 就最小的如果是1，那有没有可能我做完这个之后，它会出现 degree 0？就前面这几个。So if delta is 1, D prime looks like this, okay? Okay, so this is D prime, okay? Because we only need to find one neighbor for the smallest degree vertex. So only the first or the highest degree is decreased, okay? So is it possible that this degree sequence contains 0? So apparently D2, D3 up to Dn minus 1, they cannot contain 0 because we do not change the degree. So we only need to consider D1 minus 1. So is it possible that D1 minus 1 is 1? Oh, sorry, 0. 有没有可能 D1 那因为我减一之后，它就变成0，有没有可能？换句话说，如果 D1 减1变0，就换句话说，有没有可能 D1 是1？ 换句话说，有没有可能本来的 degree sequence 最大的 degree 是1？Yes, but I think this is a corner case, okay, because when we consider this d and d prime, we're going to assume that d has at least 3 degrees, okay, because if this is d, then we won't actually simplify it furthermore because we can just find the graph for it, okay? But that's a good point. So D has at least 3 degrees, or the length of D is at least 3, okay? Because if the length of D is 2, the algorithm will just find a graph, a kinetic graph for it, okay? So we're going to consider a long degree sequence, and my question is the same, okay? Is it possible that the first degree, which is the largest degree, is 1? And recall that our assumption is that the original degree sequence is potentially connected, meaning it satisfies these 2 conditions. So if the original degree sequence satisfies these 2 conditions, is it possible that the highest degree is just 1? If you only consider condition 1, okay? Condition 1 only says that every degree should be at least 1. So it seems like it's possible that the highest degree is 1, okay? Because at least it satisfies the first condition. But when you consider condition 2, condition 2 says that you have, it's like you have a spanning tree, okay? So imagine that you have a tree, okay? In a tree, is it possible that the highest degree is just 1? If the tree has at least 3 nodes? No, because you can consider like the root, okay? Or any vertex that is not a leaf, okay? Then it has at least 2 degrees. First to its parent, second to its child, okay? So you can always find a vertex that has degree 2, at least, okay? And another way to see this is that the total degree, sorry, this should be case 2. Okay, so this is condition 2, okay? So it's like you have n numbers, okay? And the right-hand side is 2 times n minus 1. So this is greater than n, okay? So in order for this sum to be greater than n, one of them must be at least 2, okay? You cannot have all of them being 1 and have a large degree sum. No, okay? Okay, 这边的直觉是这里 degree 上面要够大，所以 degree 上面要够大就代表你的这个 degree 基本上差不多是2倍的点的个数 ，OK， 当然会再减2，但是那个减2你可以就是有点像无伤大雅。那另外一个看法是，你可以把它想成因为我们这时候之前会之所以有那个 total degree 的 condition， 是因为我们有想到，如果是 connected graph， 它就有 spanning tree。那 spanning tree 的话，你会看到一定会有一些点，它的 degree 是至少是2的，比如说像这个 root， 像这个。OK， 那我刚刚说的是，只要你不是 leaf， 因为 leaf 的话，它就只有一个往 parent 的 degree， 但是如果你不是 leaf，那基本上你就会有至少 degree 2 ，OK。Okay. So for case 2, we need to use the second condition. Okay. So now we have that D1 must be at least 2. So D1 minus 1 is at least 1. Okay. So this means even for this case, case 2, we still satisfy condition 1. Okay. All right. So that's how we argue that there's no degree 0 in D prime, okay? Because if the smallest degree is large, then this means all degrees are large. And if all degrees are large, I don't care about this minus 1, okay? Even if I minus 1, I still get at least 1, if all degrees are large, okay? And the second case is when this degree is small, okay? But if the degree is small and the total degree is very large, this means we have some large degree. Otherwise, we cannot to make up for this small degree, okay? To make sure that we have a large total degree, and under the condition that we have a small degree here, we must have a large degree, okay? So if the degree is large, once again, I don't care about this minus 1, okay? 好，所以刚刚的 proof 就是分成这2个 case, okay? But we just finished condition 1, okay? We still need to consider condition 2, okay? So for condition 2, we have to show, once again, that the total degree is large enough, okay? So how to show that the total degree is large enough? And we can once again consider the case when delta is large, okay? And when delta is small, okay? So if delta is large, how to show that the total degree is still large enough after we simplify the degree sequence? So the intuition here is that if delta is large, okay, this means all degrees are large. This means originally all degrees are large, okay? So we have a large total degree originally. And if we have a large total degree originally, then we don't care about this small minus 1, okay? So to realize this idea, we have to find out what's the original total degree. Now because delta is the smallest degree, so we know that every degree is at least delta, and we have n delta, we have n degrees. So this is our total degree initially, okay? Now for the modified degree sequence, what's the difference between these two degree sum? 差在哪里？它们差了多少？本来是上面这个，然后现在变成下面这个，那这样子总共差了多少？前面差 delta， 然后后面差 delta， 因为这个 delta 不见了。OK。Okay. Yeah, so the first delta comes from this delta minus 1. Okay? And the second delta comes from the fact that we remove this smallest degree. Okay? Now we know that this is, because delta is at least 2, so this is at least 2 times m minus 2. Okay? And this is actually what we need, because for d prime to satisfy condition 2, because d prime has length, or let me put it this way, okay? So we want to show that the total degree is at least 2 times, but instead of using n, I'm going to replace it with the length of d prime, okay? So this d prime surrounding by this 2 vertical bar is the length. Okay, and what's the length of d prime compared to the original one? If the original one is n, and because we remove 1 degree, the smallest degree, so the length is just m minus 1. Okay? So this is 2 times m minus 2. Okay? So this is our goal. Okay? So yeah, this shows that we finished the proof for case 1. Okay? Okay. So next, case 2. So this happens when delta is 1. The smallest degree is 1. Okay. So the intuition behind this case is that if delta is 1, then we only reduce the total degree by a very small amount, that is 2, okay? Because if delta is 1, so we remove the smallest degree, which means we decrease the total degree by 1. And also we reduce the highest degree by 1. So in total, the total degree is reduced by 2, okay? Okay. So we know that by our assumption, the total degree is at least 2 times m minus 1. Okay. So this is because the original degree sequence satisfies condition 2. Okay. Now for d prime, so actually we use the same idea here. Okay. So because we minus 2 delta, but delta is 1, so this becomes minus 2. Okay, so once again, this is 2 times m minus 2. Okay. Yeah, so let's the whole proof. Okay. So I think here the key idea is to divide a proof into two cases. Case one is when the delta, the smallest degree is large, and the second case is when the smallest degree is just 1. Okay, so once you have these two cases, figure out the rest is easy. Okay. 好，我不知道到这边有没有任何问题，因为基本上跟 degree sequence 的讨论基本上就会停在这里 ，OK？ 所以整理一下，我们一开始我们考虑的问题是给你一个 degree sequence， 然后你要想办法去找一个 graph，去满足它，去 realize 它。那我们那时候有说，不是所有的 degree sequence 都可以被 realize，OK？ 所以我们先考虑一个简单的问题，去判断说 degree sequence 是不是 graphical，OK？ 然后如果大家有印象的话，我们事实上有去考虑几个规则，很简单的规则，像是 degree sum 是不是偶数，像是最大的 degree 会不会太大 ，OK？ 但这些规则其实都不是万用的，有的时候这些规则会失败 ，OK？ 就是你通过这些 check， 但是它不是 graphical， 这是有可能的，所以我们就设计一个演算法，然后那个演算法它就事实上会去那去找一个 graph 可以 realize 它 ，OK？ 然后我们接着又去看，如果我们的目标不只是要去找到 graph， 而是要 kinetic graph， 所以我们上礼拜有去看说，如果有满足2个条件，很简单的条件，当然前提是它是 graphical， 那它就一定可以被 realize， 被 kinetic graph realize，OK？ 所以我们今天刚刚做的事情是去修改我们之前的演算法，让它永远可以找到 kinetic graph， 如果 degree sequence 是 potentially connected，OK？ OK， 所以我不知道到这边大家有没有问题？关于目前 degree sequence 的讨论。嗯，对。
对，但是我们原本说的 potentially connected， 它其实应该算有3个条件吧，就是第3个应该要是第一要是 graphical。
对。
对，但有没有可能就我们满足了，就是 D prime 满足了1跟2，然后D 满足了1跟2之后，结果 D prime 却不满足，就是 graphical。
所以这个问题就是说有没有可能，所以我们要担心的事情是有没有可能本来的 degree sequence 是 graphical， 结果做完这个调整之后它变成不是 graphical， 对，但是这个就是我们在最一开始的讨论，这里就已经讨论过了，所以我们那时候有2个方向 ，OK， 所以这个方向就是你想要，就是如果本来的是 graphical， 那新的就一定会是 graphical。然后这个证明虽然说那个时候我们没有特别说我们选的那个 vertex， 可是事实上我有印象，对，就我们那时候讨论就是我们选的 vertex 就是那个 degree 最小，在 step A， 对，但是这个东西，如果你忘掉 potentially connected， 你只想要 graphical 的话，你事实上 step A 可以挑任何的 vertex 都可以。还有其他问题吗？OK， so the next topic I'm going to talk about is not strictly related to degree sequence, okay, but somehow the analysis and the proof is related to degrees. So, and also I think that the result is quite beautiful, okay? Okay. So the next topic we're going to talk about is related to this triangle-free graph. Okay, so what is a triangle-free graph? So first of all, what's a triangle? Okay, well, a triangle is like this. Okay, so this is nothing but a cycle of length 3. Okay, so this is a triangle. Okay, and what is triangle free? Triangle free means that there's no triangle. Okay, so if a graph does not contain any triangle, then it is triangle free. Okay. So I just draw a triangle like this. Okay. So let me give you some example, okay? So this is a triangle-free graph, okay? And this is not. Okay? The reason that this is a triangle-free graph is because you cannot find any subgraph that is a triangle, okay? You're not going to find one triangle in this graph, okay? But for this graph, we have a triangle, okay? Okay, so this is not triangle free. Okay. So the question that we're going to consider is, I want you to create a triangle-free graph with the most possible edges. Okay. Okay. The reason that we care about this maximum is because if you keep adding edges, eventually you're going to find triangles. Okay. But yeah, this is under the assumption that we do not increase the number of vertices. Okay, so the vertex set is fixed. Okay, so for example, here we have 8 vertices, so you cannot add any more vertices. Okay, you have 8 vertices. But if you try to add more edges to the graph, you're going to find triangles. So the problem is, how many edges can you add to the graph? Assuming that this is an n vertex graph, okay, and you do not, we do not allow triangles. So I want you to draw some examples. Okay, so I want every one of you try this. Okay, so draw, and 10 vertex graph. Okay. So if you want some papers here. Okay, so let's make it a competition. Okay, so you all have to draw a 10 vertex graph. Okay, and you have to create as many edges you can without creating triangles. Okay. See which one has the most edges. Okay.所以你需要画10个点在你的 graph 里面。And don't Google the answer or don't use Gemini or ChatGPT, okay? Just try yourself, okay? 所以你要10个点，然后不能画出三角形，然后你要尽量加越多的边越好。如果你想要的话，你可以先试试看比较更小的，比如说8个点、6个点之类的。你可以先想偶数的情况就好。So does anyone have a graph that has more than 20 edges？ 有没有人画的可以超过20个边？如果你可以画超过20个边的，举一下手。So I think you do need some kind of strategy to draw such a graph, okay? So perhaps you have to come up with a strategy and then apply the strategy to this case. Okay? So in other words, perhaps some algorithm first, and apply the algorithm to this graph, to this example. 有超过20个边的吗？有吗？还没 ，OK。所以你现在画几个边？所以对就是没有三角形。多少？25。你画了25个边。啊哈。每一个点 OK。但是你说你不确定是不是对的， 所以你是说你不确定有没有三角形在里面，是这个意思吗 ？OK。所以有其他人画超过20个边的吗？你现在画了几个边？你现在画了几个边？啊？13是不是 ？OK。应该还有蛮多可以继续画的空间，所以你画了几个边？好，那你看多小的？啊，那6的时候你画可以画几个边？哦，OK，好，那你画几个边
现在16，不过应该可以再加一点。
？OK，OK，所以你刚刚25，那是对的吗？啊哈，对，那你觉得这样有三角形吗？看起来应该没有。OK。Okay, so it turns out that 25 is the best. Okay, and the way we construct it is exactly what it said. So we're going to create two sets. Okay, which has 5 vertices. Okay, and then we'll just add edges between these 2 parts. Okay. So for every vertex in the upper part, we'll add edges connected to the lower part. Okay? So in total, we have 25 edges, okay? Because every vertex has 5 edges connected to, every vertex has degree 5, okay? Okay, so now we know that it has 25 edges. But how to argue that there's no triangle here because it's kind of messy. So 你刚刚怎么看出来它没有三角形？ Exactly. Okay. So because there's no edge between any 2 of them in the upper set. Okay. Similarly for the lower set, there's no edge connecting any 2 vertices in this lower set. Okay. So this is triangle free and 25 edges. Right, so I think it's easy to generalize this idea to other cases. For example, when n is 6, we just divide the 6 vertices into 2 sets and add edges between these 2 sets. Okay? So when n is 6, we can have 9 edges. Okay? Now the question is, can we do better? Is it possible to do better than 25 if you have 10 vertices? So if this is true, then the number of edges will be n over 2 squared. Okay? It turns out that this is true, okay? So at least when n is an even number, where you can divide the sets evenly, okay? But even if n is not even, there's only a difference of 1 between these two sets, and still this construction is the best, okay? So for example, if you have 9 vertices, you just split these 9 vertices into 2 sets. The first one has 4 vertices, and the second one has 5 vertices, and just add all the edges between these 2 sets, okay? So in total, you have 20 edges if you have 9 vertices, okay? But I think that's not the point here. So today we're going to focus on the case when n is even, where you can divide the 2 sets evenly, okay? Okay, so I think that this is the most genius proof that you're going to see for this course, okay? But it's short, okay? So that's why I want to share this with you. And by the way, this is a very famous result in graph theory, in particular in the branch called extremal graph theory, okay? So if you're interested in this kind of question, okay, you can Google it, okay? Okay. So it's not easy to direct attack this question. So we're going to reformulate the statement that we're going to prove, okay? Okay. So this is the statement that we'll actually prove, okay? So for this, we need a special handle. So the handle is the largest degree, okay? So here I use just D, okay? So D is the largest degree. So we'll show that if you have a triangle-free graph, then the number of edges you can have at most is D times M minus D, okay? So I claim that if this is true, then the original result is true, okay? This is because this product, okay? This product is maximized when D is N over 2. So the number of edges is at most N over 2 squared, okay? And this is true even for the case when n is not even number, okay? But when n is not an even number, we cannot say that the highest degree is n over 2, because if n is odd, then an odd number divided by 2 would not be an integer, okay? So we need to consider ceiling or floor function. But I think this is not important, so we'll just focus on when n is an even number, okay? Okay, so this is our goal, okay? Okay. So as I mentioned earlier, I think the proof is quite genius. So I'll just show you the proof, okay? Well, I think first of all, the fact that we know that this finishes the proof is already quite genius, because originally the goal is to prove that it's a most n over 2 squared. Okay, but we reduce this to this statement. Okay, I think this step already is quite genius. Okay. Okay, so but to use this largest degree, I think it's natural to think about the vertex that has the highest degree. Okay, so we call this vertex V. So in other words, the degree of V is D. Okay. Okay. So because we just use D to denote the largest degree. Okay, so next I'm going to draw the graph. Okay. So this is V's neighbors. And this is other vertices. Okay. So I divide the vertex set into two sets. Okay. So the size for this set is, so what is the size of this set? Or how many verses are there in this set? 这个集合里面有几个点？只确保一下大家有 follow。Okay, let me repeat. Okay, so V is a vertex that has the highest degree. So it has the most neighbors. And the degree of V is D. In other words, V has D neighbors. So what is the size of this set? D, okay? Then what is the size of this set? So I just divide the vertex into two sets. So either it is V's neighbors or it's in this set. N minus D, okay? Okay? And what's our goal? The goal is to show that the number of edges we can have is d times n minus d at most. Okay. So d times n minus d. Okay. So we're getting close to the goal, right? So we want to show that the number of edges is at most the size of this set times the size of this set. Okay. All right, but yeah, let's first take a break and yeah, I can think about how to get the relationship between the product of these two sizes and the edges. Okay. All right, so let's do this proof, okay? So recall the goal is to show that the most edges we can have is the product of these two numbers, okay, or these two sizes, okay? The size of the number of V's neighbors and the size of this set, okay? So perhaps I should first draw V, okay? So where should I draw V, okay? So V 应该要出现在上面这个 set， 还是下面这个 set？ So this is V's neighbors, right? So can V be its neighbor? No, because there's no self loop. So we cannot draw V here. So V is in this set. Okay. Okay. Now, obviously, we have some other vertices in this set. Okay. So, what can you say about this graph if I tell you that this is a triangle-free graph? Because the assumption is that we only consider triangle-free graph, okay? So if this is a triangle-free graph, are there any properties that you can see related to this picture? If there's no triangle, okay? If we do not allow triangles, then we cannot have edges in these between these any two vertices in this set, okay? Because if you have edges like this, you'll create a triangle, okay? So let me call this n of v, okay? So because it's triangle free, so this means no edge in n of v, okay? Otherwise, you'll create a triangle, okay? So this also means if there's no edge in this set, then this means every edge has at least one endpoint in this set, okay? In other words, it's like every edge in a graph is incident to this set, okay? So this is just V minus n of v. Okay. Why? Because if there's one edge that is not incident to this set, then the only place it can exist is inside n of v. Okay? But this is not impossible. This is not possible because this is triangle free. Okay. Now, if every edge is incident to this set, then I can say that the number of edges is at most the total degree of V set minus n of V. That is the total degree of this lower bottom set. And this is not equal. This is less than or equal to, because if I have an edge like this, then if I count the total degree, then I actually count this twice, okay? But here I only need an upper bound, okay? So I want to know what's the most edges, the most number of edges I can have. So I don't care about the upper bound, okay? Because the goal is to show that this is less than or equal to d times n minus d. So it's okay to have some double counting and to have some less than or equal to sign. Okay. OK， 所以刚这一步蛮关键的，就是因为我们已经有说所有的每一个边它都至少它一定会跟这个 v 扣掉 n of v 的这个 set， 就底下这个 set， 它一定会跟它相连 ，OK。所以如果我想要知道最多有几个边，我就可以去看这个底下的这个 set， 它的 degree 最多有多大 ，OK。我一定不会 miss 掉任何一个 edge，OK。甚至我有一些 edge 可能会算到2次，但是无所谓 ，OK。那我知道这样绝对是比我们真的 edge 数只会更多，不会更少 ，OK。因为我们一定不会有在上面这个 set 一定不会有边 ，OK。所以这个就是正确的上限，正确的 upper bound。OK。So now we have established that the number of edges is upper bounded by the total degree of this bottom set. So now the question is, what's the highest possible total degree of this set? So 最底下的这个 set， 它最多全部的 degree 总和最多可以到多少？ Well, it's just count what's the number of vertices here. We already have this. This is m minus d. And what's the maximum degree you can have? That's d. Okay. Okay. So let's prove. OK， 所以我会觉得这个 proof 最关键的地方应该是要把这样的图画出来 ，OK， 所以先去考虑这个 v 的邻居 ，OK， 然后再去看剩下那些点，啊，因为这个是 triangle free， 所以不会有三角形，所以一定每一个边都会是至少有一个是在底下这个 set， 那不会两个端点都在上面这个 set， 因为如果有一个边两个端点都在上面这个 set 就会有三角形 ，OK。然后我们接着就要去看说，最多的，就是 edge 数最多，事实上就可以去看它的 degree，OK。然后 degree 最多是多少，就看这个 size， 这个 set 有多大，有几个点，然后再乘上 degree 最大是多少。OK， 所以这个就是最后的结果。有问题吗？要。可以。因为它没有违反三角形的规则。你说有没有可能这样子连过来，那又这样子连过来嘛？对，但是 看一下我要怎么说。OK， 你可以把它想成这样，就是我们这边要说的事情是，如果是 triangle free 的 graph， 最多会有几个边？对，那我们这个 argument， 如果根据你的角度来想，就是这个数字，我们在得到的时候，事实上我们就连如果它有 triangle， 它也是最多是这样，有点这样的感觉。对，所以就是我们这边很多都是小于等于，所以我想最关键的是这一步。对，那所以如果我看一下哦，就整个逻辑来看的话，我们第一步建立的事情是上面这里一定不会有边，这应该没有问题。然后我们接下来建立的事情是所有的边它都一定会跟这个有相邻，但是我们从这一步开始，接下来的讨论，我们就没有管 triangle free， 我们用 triangle free 就只有用到这里而已。对，所以后面你可以说它有一点松散，但是问题是我们最多的目标就只是要去建立这个 upper bound 而已。对，但是虽然说我刚刚说是松散，会让人家觉得说，这个 n 减 d 乘上 d 这个 bound 可能会很 loose， 就是根本不可能做到这么大。但事实上，你刚刚那个 example 就也说明了，事实上，就算我们这个证明，你如果去想刚刚那些 case， 好像会有一些状况没有考虑到，或者是我们考虑，这个 proof 好像可以涵盖到这个也是 triangle free 的状况，但是结论就是 n 减 d 乘上 d， 这个真的就是可以达到的，因为你刚刚那个做法就是可以达到这个数字。对，所以这个等于是用反方向去说明说，这个不可能做到比它更好，对。所以换句话说，你也可以想成，好，如果今天有一个更厉害的人，他可以把你刚刚那个观察，就是如果他这边又加过来，那不是他就变成不是 triangle free 了吗？那你可以想象那个 proof 就会变得更复杂，但是那个 proof 变得更复杂，也不会影响最后的结果，对。所以就是有的时候，为了要让 proof 简单一点，我们可以容许像这种小于等于，对。Okay. 好，所以还有其他问题吗？n 减 d 乘上 d，OK， 就是最下面这边我们要看的是这个下面的集合的每一个点的 degree 加起来最多是多少？这个是 total degree 的意思，就是里面的每一个点看它 degree 是多少，加上它的 degree 是多少，全部加起来，就是这个 total degree of this set。那你要怎么知道它最多是多少？你就看每一个点的 degree 最多是多少。那因为每一个点 degree 最多就是 d， 因为 d 就是最大的 degree。然后因为你有 n 减掉第一个点，所以就是 d 再乘上 n 减 d。所以如果你要的话，这个是。So I think I can expand this step a little bit. Okay, so I haven't defined this term precisely, but for this term, we just sum up all the degrees for the vertices in this set. Okay, so this is V minus n of V, so this is the bottom set. Okay, and we consider all the vertices in this set, and we compute the sum of their degrees. Okay. Now, because we know that the highest degree is D, so we know that D of V is at most D. Okay? So now you see that this term is not related to V, so this is just, you can take out D and sorry. Okay. Okay, so for every element in this set, it just contributes 1. Well, so this summation is just the size of this set. Okay, so the size of this set is n minus d. Okay. So the result is that the total degree of the lower set is at most, because we have this less than or equal to sign here. So the result is that the total degree is at most d times n minus d. Okay. 还有其他问题吗？就 OK 吗？如果有任何问题就直接问就可以了。对，有吗？哪页？Sorry。哦。哦，这里吗 ？All right. So, what's dV? So this is the degree. Well, I think I should use a different notation because here V is reserved for the vertex with the highest degree. So I'll change it to U, okay? I'm not sure whether this causes your confusion. All right? So D of U is just the degree of U, okay? And what is D? D, according to our previous definition, D is the largest degree, okay? So in other words, d of u is like the degree of some vertex. I'm not sure which vertex, but I know that since this is a vertex in a triangle-free graph, I know that this is at most delta. Oh, sorry, d. Okay. Good. So anytime you have any question, just ask. Okay. So I think this definitely helps our students. 所以有任何问题就问就对了。还有其他问题吗？ And for the rest of this part, this is just like this, okay? So you have some set times some number c. That's not times, okay? And for each element, you just add c to the summation. So this is just c times the size of the set. Okay. So for example, if I replace the c with 3, so this is just 3 times the size of s. Okay. So this is just what we do here. Okay. Any other questions? 자, 지라우님아. All right. If not, let's move on to the next topic. So I think with that, we've concluded our discussion related to degrees. Okay. I think this only serves as like a warm-up for the whole semester because degrees, well, this is kind of the fundamental concept in graph theory. Okay. So next we're going to start to discuss, I'll say the first important topic in our course. Okay, that is matching. Okay, so let me first define, or let me first give you an example. Okay. Okay, so this is a graph, okay? So a matching is just a set of edges, right? So we want to match vertices. And we cannot just arbitrarily match edges. We can only match match vertices if there's an edge between these two vertices, okay? So for example, I cannot match these two vertices because they are not adjacent, okay? So only adjacent vertices can be matched, okay? So that's why I said that matching is a set of edges, okay? But we need to consider some constraint, okay? Because you do not want to match a vertex to multiple vertices, okay? So for example, if I already match this guy in the center to this guy, then I cannot match this guy also to this vertex, right? Because it's matched to two different vertices, okay? So this is not allowed, okay? So this is not a matching, okay? So that's basically all the constraint for matching. So matching is a set of edges, and these edges cannot touch each other, or they cannot share endpoints, okay? So for example, if you have this edge in your matching, then next I think perhaps you can add this edge, okay, and this edge, okay. So this is a valid set of edges to form a matching, okay. So in this case, we just said that this matching has 3 edges, okay. Okay. So before we can start to talk about matchings, we have to first have a graph, okay? So after we have a graph, we can define a matching based on a graph. So a matching is just a subset of edges, okay? A subset of the edge set E, all right? And these edges, they cannot touch each other. So the first theme, or the first important question for this course, is to find the largest matching, okay? Okay. For example, for this graph, we have 3 edges. Is it possible to find a larger matching? For example, like 4 edges. So how? Let's put A, B, C, D, E, F, G, H, okay? So how to create a larger matching? Oh, there are 2 Fs, sorry. A, B, C, F, G. Sorry. A, B, and D, E, C, F, A, B, D, E, C, F, and G, H. Okay. So yes, so this is a larger matching, okay? So this matching has 4 edges. So we can ask the same question again. Is it possible to find a larger matching? Now we have 4. Is it possible to have 5? No, so why? All right, okay, so if there's only 8 vertices, then you can have at most 4 edges in the matching. Okay, so this is indeed the best. Okay. So I don't have enough time to discuss algorithms for this problem. By the way, this is called maximum matching problem. Okay. Okay. So there's a very similar concept, okay, called maximal matching. Okay, so just like when we discuss components, recall that we said that the component is a maximal connected subgraph. Okay, and I said earlier that whenever you see some words ending with AL, you should think about local, LOCAL, okay? So maximal matching is like a local maximum matching, okay? This is not the best globally, but locally it is the best, okay? So what do I mean by locally, okay? So a matching M is a maximal matching if there's no larger matching that contains it. Okay? By contains it, I mean there's no larger set of edges that take M as a subset, okay? So for example, so this green edge, this green matching is a maximal matching because, so perhaps I can give you another definition. If you cannot add any more edges to M, okay? So if you cannot add any more edges to it, okay? But still the constraint is that after you add the edges, it is matching, okay? So if you cannot do this, then it's a maximal matching because by definition, if it's a maximal matching, this means you cannot find a larger set which contains all the already existing matching in M plus some other edges, okay? So if we consider these green edges, we can consider every other edges that are not green, okay? For example, like this one. So given these green edges, can we add this yellow edge while maintaining a matching? No, because if we add this edge, then these two edges, they will share the same endpoint, okay? So we cannot add this edge. Similarly, we cannot add this edge, and this edge. So I think it's easy to see that once you have these 3 green edges, you cannot further add any more edges. Therefore, these green edges, they form a matching, a maximal matching, okay? So I think it's very easy to find a maximum matching, okay? You just keep adding edges, okay? But when you add edges, you have to be careful that you cannot add edges that will touch other edges that you've already chosen, okay? So this is a very simple algorithm. So you just choose any edge, in the graph, okay, and add it to the matching. Okay, and after you add the edge, for example, if I have this graph, okay, and suppose the first edge I choose is this edge, okay, so this is E, okay, so after I choose this edge, because I have to make sure that the final output is matching, I have to make sure that I won't choose edges like this one, this one, this one, this one, or this one. In other words, I cannot choose edges that are adjacent to this edge. So a very simple way to achieve this is that after I choose this edge E, I just remove all the adjacent edges. Okay. Okay, and I just repeat until all the edges are removed. And also I have to remove E because E is already chosen, so I cannot choose E again. Okay. Okay, so if I apply this algorithm, then this one, this one, this one, this one, and this one are gone, okay? And next I can choose, for example, this yellow edge, so I have to further remove this one, okay? And then I can choose this edge, then I have to remove this one, and then I can choose this one, okay? And at this moment, either every edge is either chosen or removed, okay? All right, so this is how you get maximal matching. Pretty straightforward, okay? But not, at least from this example, we know that a maximal matching is not necessarily a maximal matching. Oh, sorry, a maximal matching is not necessarily a maximum matching, okay? Because it is just local maximum, okay? Okay, so I only have 10 minutes left. So I want to show you that even though this is not maximum, okay, even though this is not the best, it is still, in some sense, close to the optimal solution, close to the maximum matching, okay? So my question is the following. Say there are 10 edges in the maximum matching. So maximum matching, 10 edges. Is it possible that the maximum matching you find only contains, say, 3 edges? Is it possible? 有没有可能 maximum matching 超级大，比如说10个 edge， 但是你选的 maximum matching 只有3个边，或2个边，或1个边，或4个边，有没有可能？ So I want to show that maximum matching cannot be too small compared to the maximum matching. So I'm going to show that maximum matching or maximum matching the size of the maximum matching is at most twice the size of the maximum matching. Okay? So if the maximum matching has 10 edges, then the maximum matching has at least 5. Okay? So you cannot have only 3 edges in your maximum matching if the maximum matching has 10. Okay? So the ratio between these two sets, 2 at most, okay? So can you see why? 为什么最多差2倍？ So throughout this course, we're going to use M star to denote the maximum matching, okay? And we'll use M to denote other matching, like this maximum matching, okay? So let's draw M star, okay? So M star has 4 edges, okay? So the key observation is, so this is M star. Is it possible that the maximum matching does not use this and this vertex? In other words, is it possible that the edges in M do not touch this and this? 有没有可能 maximum matching 完全没有碰到这2个点？所以为什么不可能？ Exactly. Okay. So the key observation is that the maximum matching must touch at least one of them. Otherwise, if M does not touch this and this, if both of them, they are not endpoints for the edges in M, then actually I can add this edge to M, and it will still be a matching. So this will violate our definition for maximum matching because this is not local maximum, because we can still add this edge, okay? So this means for every edges, so for every edge in the maximum matching, M, the maximum matching, at least it touches at least one of the endpoint. Okay? So, in other words, M touches at least M star vertices. Okay? So back to our previous example where the maximum matching has 10. So if it has 10 edges, we know that the matching can touch at least 10 vertices. Okay? So if I tell you that a matching touches, say, 4 edges, 4 vertices, what is the smallest possible number of edges you use to touch 4 vertices? 如果你有4个点，那我跟你说你的 matching 这4个点都有碰到，那请问你的 matching 至少会用几个？最少是用几个边？如果你有4个点，你要去 touch 这4个点。This 4, okay? So if I want to create a matching to touch these 4 vertices, well, first of all, I can definitely do this, okay? So for every vertex, I use a separate edge to touch it, okay? But this is not the most efficient way, okay? So actually I can do just 2, okay? So for every 2 vertices, it's possible that I can use the same edge to touch both of them, okay? So if M touches at least this many vertices, I know that M has at least the size of M star over 2 edges. Okay. The reason we have this 2 in the denominator is because for every 2 vertices, we can just use 1 edge to touch both of them. Okay. Okay, so if M has at least this many edges, this is basically our result, our desired result. So M is at least M star divided by 2, okay? So you just switch these 2 in the denominator to the left-hand side, you get the desired result. Okay. So even though we haven't discussed how to solve the maximum matching problem here, but we already have a, I'll say, decent algorithm because this is a very efficient, very simple algorithm. We just compute the maximum matching. And we know that this is not very far away from the maximum matching because the factor between these 2 matching is at most 2, okay? Or the ratio between these 2 solutions is at most 2. Okay. All right, so let's call it a day. Are there any questions? 有问题吗？对，就是我们还没有讲真的 maximum matching 要怎么做，这个我们可能会需要花2-3个礼拜，包含这个演算法的正确性的分析等等。当然我们这边至少看到一个很简单的演算法，就是有点像一个 greedy 的演算法，你就选了一个边之后，你就随便选一个边，然后把跟它相应的边都删掉，再随便选，就一直做，OK， 非常的简单。那这种 maximum matching 呢，虽然说不一定是最好，但是它最多跟最佳解就不会差超过2倍。Okay, so that's it. Okay.